Okay, so maybe we have Dingyu to tell us on Morse theory to Hamiltonian flows, which lead to Arnold conjecture.
So, good afternoon, Dr. Chang and Dr. Ni. My name is Pangdingyu, and the topic of my FYP is From Morse Theory to Hamiltonian Flows, a Path Toward the Arnold Conjecture. So let's first look at the motivation of what is Arnold conjecture. So Arnold conjecture provides a lower bound for the number of one-periodic solutions of a time-dependent Hamiltonian system. We will first discuss the classical Morse theory, which gives similar bounds for critical points of smooth functions. And our goal is to extend Morse theory to infinite dimensional loop space to study Hamiltonian flows. And finally, we will introduce the flow theory, which provides a framework to define a Morse type homology for the action functional. First, we need to know what a Morse function is. So if we are given a smooth function from a smooth manifold, a point x is called a critical point if the differential evaluated at x is 0. And also we have to define the Hessian of f, which is defined as a symmetric bilinear form d2f, such that for any two tangent vectors, we will have this formula where y tilde is an extension of y on neighborhood of x. And then we define a critical point x to be non-degenerate if we know the Hessian at x is invertible. That means the determinant is non-zero. And finally, a Morse function is a function whose critical points are all non-degenerate. Then let's look at the Morse lemma. The Morse lemma states that suppose we have a non-degenerate critical point C, then there exists an open neighborhood U of C and a diffeomorphism psi such that psi vanishes at 0, vanishes at C. That means it centers at C. And if we compose psi inverse on F, we will get this quadratic form. And if such coordinate chart exists, we will call it a Morse coordinate chart for F centered at C, and we will say the integer I to be the Morse index or simply index of C. Then we want to define the pseudo-gradient field to describe how the flow lines are look like to connect the critical points. So a pseudo-gradient field is a vector field V satisfying these two conditions. So the first condition saying that the differential of Vx is always smaller than or equal to 0 is non-positive, which means that we are actually defining negative gradients, lack of negative gradients. And the equality occurs if and only if x is a critical point of f. And the second condition is that our vector field V must agree with, which means it's coincide with the negative gradient vector field on neighborhoods of critical points of F. Then let's define the stable and unstable manifold. So if we have a critical point of a Morse function, which is C, and we define the unstable manifold of C as the points in M such that x goes to C when t goes to minus infinity. In other words, the flow line starts at C. And on the other hand, the stable manifold consists of points whose flow lines terminates at C. That's why it's called stable manifold, because the flow line terminates there, is the termination, is the endpoint. So it's stable there. And here's a remark. If C has an index lambda, then the dimension of the unstable manifold of C is lambda, and the dimension of the stable manifold of C is n minus lambda. This is quite intuitive if we look at the Morse lemma here, because this part corresponds to the unstable manifold, and this part corresponds to the stable manifold. As we can see here, we have dimension I, and here we have dimension n minus I. And of course, rigorous proof is needed, but it's not stated here, and it can be found in my paper. So next, I will introduce a property of a pseudo-gradient field. So we say a pseudo-gradient field satisfies the Smell condition if for any pair of critical points A and B, we have the stable manifold of A intersects transversely with the unstable manifold of B. So if a pseudo-gradient field satisfies this condition, we call it satisfy the Smell condition. And in fact, not every pseudo-gradient field satisfies Smell condition. That's why we will introduce this Kupka-Smell theorem, which grants a pseudo-gradient field close to, in fact, C1 close to V that satisfies the Smell condition. Therefore, we can make the assumption that our pseudo-gradient field satisfies the the Smell condition. And formally, it says that for any pseudo-gradient field V adapted to F, there exists a pseudo-gradient field V prime, which is C1 close to V coincide with V on the neighborhoods of critical points of F and satisfies the Smell condition. So the proof can be found in Altin's book in this reference. And then we want to define the Morse complex. So the Morse complex is defined as a pair, of course, C star partial, and we define CK be the vector space consisting of all linear combinations of critical points of index K. And we take the coefficients from Z over 2 instead of Z because we want because Z over 2 is field and we need some properties from fields. And also of course we need to define the differential. The differential is defined as a linear combination of critical points of dimension of index K minus 1, where the coefficient NAB is the number of trajectories module 2 from A to B on V. And one may ask that, is it really a complex? So we need to prove that the partial squared is indeed 0. So let's take critical points of index K plus 1, and we evaluate here by the definition of our definition of differential. We can expand it into this expression. And therefore, it suffices to show that the inside part is congruent to 0, module 2 is 0. So it suffices to show this part is 0 for each critical point of dimension of index K minus 1. And to show this, first we denote MXY as the moduli space consisting of trajectories from X to Y. And we assume V satisfies the Smell condition, which is authorized by the Kupka-Smell theorem. Therefore, we will have this transversal intersection. There is a very common property of transversal intersection about the dimension of them. So we can apply it in our case. So we get it here. We have the dimension of this intersection is equal to dimension of WUA and plus dimension of WSC minus N. So the unstable manifold of A, by our remark just now, we know that its dimension is K plus 1. And the stable manifold of C, we know that it's N minus the index of C, which is N minus K plus 1, N minus K minus 1. Therefore, if we evaluate this, we will see that the answer is actually 2.
What is the N here?
I'm sorry. N is the dimension of the whole manifold. I mean, M1 and M2 are two submanifolds of a manifold, and N is the manifold. So N here is just the dimension of W of the symplectic manifold. Okay. And then by quotient manifold theorem, the condition is easy to check because we can easily construct an action satisfying the conditions. So we can apply the quotient manifold theorem. So we will see our moduli space is a manifold of dimension 1. Then we want to compactify our moduli space. So to compactify moduli space, we want to know what its boundary point, what its boundary is. So in fact, the boundary turns that the boundary point of the moduli space is the broken trajectories from A to B, and then go to C. So we can see it intuitively here because we have flow lines from A to C, and if we take the limits of it, we will get the limits, the broken trajectories. So that's the intuitive interpretation of why the boundary points are these broken trajectories. And now we have a M bar AC, which is a compact one-dimensional manifold with boundary. And we know that the number of boundary points of a compact one-dimensional manifold with boundary is even. This is because such manifold must be a disjoint union of closed intervals and S1, the circle. So the number of boundary points must be even. And therefore, the summation we want is equal to the number of broken trajectories, and of course is congruent to 0 modulo 2. And then let's define the Morse homology. There's nothing special. We just define Morse homology as kernel del over image del. And we consider the theorem saying that the Morse homology depends neither on f or v. If you admit this theorem, we can denote the Morse homology modulo 2 of M as this notation, because we know the Morse homology depends only on the manifold M. Yeah, so I think I have to skip this proof, but the main idea of this proof is that we will show that if we have two chain complexes on the same manifold, then we can always construct a chain map between the two complexes. And of course, it's an isomorphism, and it induces an isomorphism between their respective homology groups. So, yeah. Then is the Morse inequalities. So first we define the Betti number to be the dimension of case homology group. And the Morse inequalities states that the number of critical points is larger than or equal to the summation of Betti numbers. So the proof is quite easy, actually. Our CKF by definition is dimension CKF, and we know kernel del K, since del K has domain, the domain of del K is exactly CKF, so it must be smaller than the dimension of CKF is kernel. And we know that the homology group is equal to kernel del K over image del K plus 1, so it's also smaller. So therefore, we finally have CKF is bigger than or equal to the Betti number beta K. And if we take summation on both sides, we will get the Morse inequalities. Then let's introduce the autonomous and review the autonomous and time-dependent Hamiltonians. So Hamiltonian, let H be a smooth function on a symplectic manifold. The Hamiltonian vector field is defined by this formula. Iota omega on xh is equal to minus dh. And we call H an autonomous Hamiltonian. We call it autonomous because it doesn't depend on time t. On the other hand, if the Hamiltonian do depend on time t, we call it a time-dependent Hamiltonian. And we will denote its associated Hamiltonian vector field to be xt equal to xht. And then we have to define the periodic orbits. So periodic orbits is a trajectory of the flow phi of xh on which each point x satisfies phi1 x equal to x. In other words, it means that x is a fixed point of phi1. So note that we can also use x to represent the whole periodic orbit. So It's so we'll use a little abuse of notation here. So X can also represent the whole periodic orbit, as in the next definition, we say a periodic orbit X is said to be non-degenerate if the differential phi1 at the initial point x0 has no eigenvalue 1. So in math language, it means that the determinant of the identity matrix minus tx0 phi1 is non-zero. Now let's introduce the Arnold conjecture. So Arnold conjecture states that if we have a compact symplectic manifold and a time-dependent Hamiltonian function, and we further assume that all one-periodic solutions of the associated Hamiltonian system are non-degenerate, then the level of such one-periodic solutions is bounded below by this summation. Note that this summation is exactly the same what we met in Morse inequalities. And actually, we will use analogous strategy to find this formula here, as in the Morse case. Then I will briefly introduce the floor theory. So floor theory is basically the infinite dimensional version of Morse theory. And similar to the Morse theory, we have a finite dimensional manifold. Here we define a loop space on a symplectic manifold. LW is defined as all smooth contractible loops on W. And as we can see, it is an infinite dimensional manifold, and which is different from what we met in Morse theory, as we discussed on finite dimensional manifold. And then we define an action functional AH on the loop space defined by this expression, where, of course, since we are integrating on a disk D, we need to extend X to, we need to find an extension of X, which we call U. And our goal is to define a complex whose generators are the critical points of the action functional AH. So one direct question is, why do we define the action functional in this way? So the next theorem tells the answer that loop X is a critical point of AH if and only if a periodic solution of the Hamiltonian system, it is a periodic solution of the Hamiltonian system. So if we admit this theorem, we can convert our question that counting the periodic solutions of the Hamiltonian system to counting the critical points of AH. So the theorem is, the proof is also not that hard. We will compute the differential of AH at a tangent vector yt. We first take a yt, and we will make the following extensions. I will skip it here. And we compute the differential of AH at yt in this way, and we expand XH by its definition. We can get it into these two parts, and we evaluate those two parts one by one. We can get the first term here by definition of Lie derivatives and Cartan metric formula. And the trick here is to use Stokes theorem to integrate on S1 instead of the whole D. So by Stokes theorem, we can make our question easier. So it can be written like this, and by the anti-symmetric of omega. The second term is easier because we can, by definition, find the DHT here. And by definition of Hamiltonian vector field, we write it into this form. If we combine these two terms, we will get this expression. And as we can see, DAHX is equal to 0 if and only if we have this part equal to 0, which means X is a periodic solution of the Hamiltonian vector field. Then I will introduce the floor equation. So a very brief review of Morse theory. In Morse theory, we use the solutions gamma of the gradient field equation. This equation, where V is a pseudo-gradient field, to describe the relationship between critical points and the Morse function. And in Morse theory, we analogously need two concepts. The first concept is almost complex structure. So almost complex structure is a smooth endomorphism J on TW, such that for each P, we have JP squared is equal to minus identity, which means it's a complex structure, and omega JPV JPW is equal to omega VW, which means JP is symplectic. And also we want this map VW to omega V JPW to be a positive definite inner product on V. So if these three conditions are satisfied, we call J a almost complex structure. So then in analogy with the Morse case, we define the negative gradient flow of the action functional AH by setting this equation. And by substituting AH by its definition, it's not hard to see that these two so then we are interested in the solution space of the flow equation. So for solution to the flow equation, first we need to define its energy, be this integration of D or dsAHU. And by chain rule, we can also write it in this form. Let M denote the space of smooth contractible solutions U to the flow equation that have finite energy. So why do we interested in only finite energy? So the theorem states that a solution to the flow equation has finite energy if and only if it connects two critical points x and y of the action functional AH. And to show this theorem, the backward direction is quite simple, because if we know a solution U connects x and y, then we must have the energy is directly AHX minus AHY, which is of course finite. And the forward direction is much more complicated, and it can be found in this paper and not be shown here. Then we want to construct the flow complex. First, we need a Maslov index. This construction is also complicated, but the main idea is to use linear algebra. And what we should know is that it is defined for only for contractible non-degenerate periodic solutions of the Hamiltonian system. And as we can see, the construction of the definition of the complex is exactly the same as in the Morse case. This is a direct sum of Z of 2Z times H, and this one is also the same as the Morse case. And we call this a flow complex. And using techniques analogous to those in the Morse complex, it can be shown that mxy is a manifold of dimension mu x minus mu y by transversality, which we have shown just now in Morse case. And so given we have mu x minus mu y, we can compactify mxy over R to one-dimensional manifold with boundary, whose boundary consists of broken trajectories. And in conclusion, we must have partial square equal to 0, yielding the flow complex is well defined. And of course, we want to define the flow homology, nothing special, just to use this quotient, kernel del over image del. And similar to Morse case, it turns out that the flow homology does not depend on the choices of H or J. So actually, it neither depend on the Hamiltonian nor the almost complex structure. And then a key property is that the Morse homology and flow homology are actually coincide under some conditions. So if our Hamiltonian H is autonomous and C too small, and or its non-degenerate one-periodic orbits are constant, we can find a natural isomorphism between the flow homology and Morse homology. Note that here is a shift of n, but it doesn't matter because we are only interested in the structure of them. The key step is that So to show this isomorphism, the key step is that under these assumptions, we need to show flow trajectories coincide with Morse gradient trajectories. So this allows us to find a chain map here. And as a result, the two homologies must be naturally isomorphic. So in conclusion, since we know the flow homology coincide with the Morse homology, the Morse inequalities can be applied to the action functional. And therefore, it is a direct conclusion to the Arnold conjecture in this case. So in conclusion, flow theory extends Morse theory to infinite dimensional settings, and Arnold conjecture relates fixed point of Hamiltonian flows to the topology of the manifold. And in the autonomous C2 small case, flow homology can be shown to coincide with the Morse homology, providing the proof of the Arnold conjecture in this setting. And the key idea involved is that the action functional on loop space, the flow equation, and compactness and transversality. And finally, flow theory provides a powerful framework with deep applications in modern symplectic geometry and low-dimensional topology. This is all of my presentation. Thank you for listening.
Okay, we have 3 minutes left. So Qinghao, do you have more questions?
Okay, so I have a question why is the symplectic structure important? And if I am correct, that you only first begin with a symplectic structure and then you have a complex and then you have a homology, and later you can choose different J, that's I think 10 at this 10, and then but it turns out that J doesn't matter. For different J, you can get another different complex, but it will be the same with the original homology from the symplectic structure one, right? So like my
Yes,
question is why is the symplectic structure important here?
because the symplectic structure allows us to do many variations here. Because, for example, see you mean the symplectic structure, right? Since we need to use its non-degeneracy and anti-symmetry and many of its properties as we are interested, because you see, like here, we do need a symplectic structure to complete this proof. Here, we use many of its properties, like here, anti-symmetry, something, and here it's closed, something.
I mean, the action function is defined by the symplectic structure, right?
The flow,
Action,
right?
The action functional.
yeah. Action functional is depend on, yes, action functional is depend on the structure, symplectic structure. I mean symplectic structure or complex structure.
Okay, so in short sentences is if the J is like controlled well by the symplectic structure, the second homology will be the same with the first homology, right? Can I say that?
The second homology
Like
and
you
the
have
first homology.
like the flow complex and flow homology, right? If if the J is like 10, you see like the third is positive definite, but yeah, it's
Okay.
somehow controlled well by the symplectic structure, then your flow homology will turns out to be the same with the Morse homology. Yeah.
Yes. Yeah.
Yeah. I
Mm.
think that's what's going on here. This is not any almost complex structure. It has to be controlled well by the symplectic structure in some sense.
Okay, so we call it calibrated by omega because it really related to
Yeah.
the
It's
symplectic. Yeah.
well controlled by omega, by the symplectic structure. So
Yes.
their topology should be the same. Yeah.
Yeah.
Okay. So that's my
Yeah, I think in the original construction, Floor used Lagrangian, so there they consider a family of almost complex structure. I'm not sure, maybe Syed will talk about that. Is it? Do you know whether Syed will talk about family of almost complex structure?
I don't know much about his presentation.
Okay. Yeah. But in the original construction, actually they consider family of almost complex structure, which are well defined. Maybe it's tame.
Yeah. So I think they're like a more wild scenario, but this is just the best thing. So the topology will be the same, that kind of thing. Okay, thank you. I have no problem.
Thank you, Professor. Bye bye.
Bye bye.
Bye bye.